Steam slowly rises from the surface, twisting gently into the air. The cup is perfectly ordinary. Ceramic walls, a curved handle, a little warmth spreading into your hands. Nothing about the moment seems mysterious. Then your elbow moves just a little too far. The cup slides. For a brief moment it balances on the edge of the table, almost as if the universe is deciding what happens next. Then gravity wins. The cup falls, hits the floor, and shatters into dozens of sharp fragments that scatter across the room. Everyone watching understands exactly what just happened. It feels normal, natural, almost boring. Cups fall and break. We have seen it thousands of times. But something very strange is hidden inside this simple event. Think about what we never see. You have never walked into a kitchen and watched pieces of ceramic suddenly slide across the floor, jump together, fuse perfectly into a coffee cup, leap onto the table, and fill themselves with hot coffee. No one has ever seen that happen. Not once in the entire history of human observation. Yet if you think about it carefully, the laws of motion themselves don't obviously forbid it. If you film the cup falling and shattering, you can play the video backward. When you watch the reversed video, the pieces gather themselves together and reconstruct the cup before it jumps neatly back onto the table. The motion itself doesn't look impossible in terms of physics. The fragments simply move in certain directions, collide in certain ways, and assemble. The equations that describe motion often work just as well forward as backward. So here is the strange question hiding inside the broken cup. Why do we only ever see the movie playing in one direction? Why does the cup fall and shatter, but never unshatter? Why does time seem to move forward, but never backward? At first glance it seems obvious. We say things like, that's just how the world works. But in science, saying something is obvious is usually a sign that we have not looked carefully enough yet. Physics tries to understand the deepest patterns behind ordinary experiences. And the broken coffee cup turns out to be one of the most powerful examples we have for thinking about time itself. The cup falling is not mysterious. Gravity explains that part perfectly. The earth pulls the cup downward, the floor stops it suddenly, and the ceramic structure cannot survive the stress. The result is fragmentation. But the deeper mystery is not the breaking. The mystery is the direction. Events seem to unfold in a particular order. First the cup is whole, then it falls, then it breaks. After that, the fragments remain scattered. The order never reverses. Our entire experience of reality follows this same pattern. Eggs break, but never unbreak. Smoke spreads through a room, but never gathers itself back into a cigarette. Ice melts in warm water, but warm water never spontaneously forms perfect ice cubes. Everywhere we look, the same rule appears. The past is different from the future. The past contains things that were more organized. The future contains things that are more disordered. And the broken coffee cup is a perfect example. A single solid object becomes many scattered pieces. Order becomes disorder. That simple change hides one of the deepest laws of the universe. Physicists eventually discovered that this tendency toward disorder is not just about cups or eggs or smoke. It is woven into the fundamental behavior of matter itself. Understanding why broken cups never reassemble will eventually lead us into one of the most important ideas in physics, the concept of entropy. And once you understand entropy, something remarkable happens. The broken coffee cup stops being just a kitchen accident. It becomes a clue about the direction of time, the history of the universe, and the reason traveling into the past may be far more impossible than science fiction ever imagined. To understand why the broken coffee cup never reassembles, we need to explore a very important idea in physics. Scientists call it entropy. The word may sound technical, but the idea behind it is surprisingly simple. Entropy is essentially a way of describing how ordered or disordered something is. Think about a brand new deck of playing cards. When the deck is fresh, every card is arranged in a very specific order. Ace, 2, 3, 4, all the way through the suits. That arrangement is highly organized. But the moment you start shuffling the deck, the order disappears. The cards become mixed. Once shuffled, there are an enormous number of possible arrangements the deck could be in. The interesting part is this: there are far more messy arrangements than perfectly ordered ones. In fact, The number of disordered possibilities is so overwhelmingly large that when you shuffle the deck, it almost never returns to its original perfect order. Nature behaves in a similar way. Imagine your bedroom after you clean it. The bed is made, clothes are folded, books are neatly arranged, and everything is exactly where it should be. That neat arrangement represents a very small number of possible states for the room. But if you live in that room for a few weeks without cleaning, things slowly change, clothes move, dust appears, books get misplaced, objects spread across the room. The number of messy arrangements is enormous compared to the number of neat ones. Because of that, disorder tends to increase naturally. It doesn't require any special force. It happens simply because there are more ways for things to be messy than there are for them to be perfectly organized. This simple idea is captured in one of the most important rules in physics, called the second law of thermodynamics. The law says that in an isolated system, entropy tends to increase over time. In other words, systems naturally move from more ordered states toward more disordered ones. Now return to the coffee cup sitting on the table. When the cup is whole, all of its atoms are arranged in a very precise structure. Ceramic is a solid because its atoms form a stable lattice. Each atom sits in a particular position relative to its neighbors. This organized structure is what gives the cup its shape and strength. But when the cup falls and shatters, that structure is destroyed. The cup becomes many separate fragments scattered across the floor. Each fragment contains atoms still arranged locally in solid form. But the overall structure of the cup is gone. Here is the important part. There are countless ways those fragments can lie on the floor. They could spread out in different directions, land at different angles, bounce in slightly different ways, or break into slightly different sizes. Every tiny variation produces a new possible arrangement. But there is only one extremely specific arrangement in which all those pieces fit together perfectly to form the original cup again. So from a purely statistical point of view, the broken state is vastly more likely than the intact one. The universe does not prefer disorder in the emotional sense. It simply moves toward the states that have the greatest number of possibilities. When a system evolves randomly under the laws of physics, it almost always drifts toward the arrangements that can occur in the largest number of ways. That is why eggs scramble easily, but never unscramble themselves. It is why perfume spreads through a room, but never gathers itself back into the bottle. And it is why a shattered coffee cup remains shattered. The increase of entropy is not just a rule about broken objects. It is a statistical property of matter itself. It emerges from the fact that the microscopic particles making up the universe can arrange themselves in astronomically many ways. And among all those possibilities, disorder overwhelmingly wins. Let's return to the broken coffee cup and think about what happens after it hits the floor. Before the fall, the cup exists in a very specific, highly organized state. Every atom is arranged neatly within the ceramic lattice. The molecules of the coffee are contained warm and almost perfectly ordered compared to the chaotic possibilities in which they could exist. The entire system, the cup, the coffee, and even the surrounding air, is in a relatively low entropy state. Low entropy simply means high order, a carefully organized arrangement that is extremely unlikely to occur by chance. When the cup falls, energy from the impact spreads throughout the cup and the surrounding environment. The ceramic structure can't absorb that energy perfectly, so it breaks. Fragments scatter. Some pieces rotate, others bounce. Tiny cracks propagate, changing the exact positions of atoms and molecules throughout the material. The coffee splashes, the heat disperses, and the fragments come to rest on the floor. In that instant, the overall system has moved from a low entropy, highly ordered state to a high entropy, disordered state. There are now far more ways for the atoms and fragments to exist in this broken state than in the original cup. The broken arrangement is statistically far more likely than the intact one. The key point is that nature does not actively prevent the cup from reassembling. The laws of physics, Newton's equations for motion, Maxwell's equations for electromagnetic forces, and even the equations of quantum mechanics don't forbid the fragments from moving in exactly the right way to reconstruct the cup. In theory, if each piece somehow traveled along a precise path, collided with perfect timing, and restored every atom to its exact previous position, the cup could reassemble. Yet this is where probability dominates reality. The number of ways the fragments could remain broken is astronomically larger than the single arrangement in which they form a perfect cup again. The likelihood of spontaneous reassembly is so close to zero that it is effectively impossible. This is why the arrow of time becomes visible in everyday life. Events unfold in one direction because the universe tends to evolve from less probable, ordered states to vastly more probable, disordered states. Broken cups remain broken. Smoke spreads and never contracts. Ice melts and never spontaneously forms. Forward in time corresponds to increasing entropy. Backward in time would correspond to decreasing entropy, an event so improbable that it never occurs in practice. Even the smallest mistake in coordinating the motion of fragments would prevent the cup from re-forming. Every air molecule, every vibration of the table, every tiny fluctuation in temperature would need to cooperate perfectly to reverse the process. The number of variables is unimaginably large, and the statistical chance that they all align is essentially zero. In that sense, the universe is not making a moral choice to prevent time from reversing. It is simply following the overwhelmingly likely path toward disorder. This principle scales beyond coffee cups to every part of our universe. Galaxies, stars, and planets all evolve toward higher entropy configurations. Life itself ages and decays. Entropy governs everything from the microscopic scale of atomic arrangements to the vast scale of cosmic structures. The broken cup is not merely a kitchen accident. It is a window into one of the most fundamental aspects of reality. By studying why broken objects do not spontaneously rebuild, we begin to understand the deep statistical rules that shape the flow of time itself. In short, the world looks the way it does because it overwhelmingly follows the path toward disorder. Low probability, highly ordered arrangements exist only briefly and naturally degrade into higher entropy configurations. The broken coffee cup is one of the clearest and most relatable examples of this universal tendency. It shows us why certain events only happen one way and provides the first tangible hint of why time has a preferred direction in the universe. Now that we understand how entropy explains why broken cups never reassemble, we can explore one of the most profound concepts in physics, the arrow of time. Time, as we perceive it, has a clear direction. We remember the past, experience the present, and anticipate the future. Yet fundamentally, most physical laws do not distinguish between past and future. Newton's laws, for instance, work equally well whether time moves forward or backward. If you film two billiard balls colliding and play it in reverse, the motion still obeys Newton's equations. Maxwell's equations governing electricity and magnetism are also time-symmetric. Even at the level of quantum mechanics, the core equations do not prefer one temporal direction over the other. So why does reality feel different? Why do we always see cups shatter, but never spontaneously reassemble? The answer lies not in the laws themselves, but in the statistical behavior of large numbers of particles. When we deal with a few particles, time symmetry is plausible. But in systems containing trillions of particles, like a coffee cup, the coffee it holds, and the air around it, the statistical probabilities dominate. Low entropy, highly ordered arrangements exist only briefly and are extremely rare. High entropy, disordered arrangements are overwhelmingly likely. As a result, the macroscopic world develops a clear temporal direction. Events progress from less probable, ordered states to more probable, disordered states. This is what physicists call the arrow of time. It is the direction in which entropy increases. It is the reason we see smoke spread through a room, but never gather itself back into a candle. It explains why ice melts in water, but warm water does not spontaneously form perfect ice cubes. It governs every everyday process, from cups breaking to aging to the expansion of the universe. Entropy creates a statistical bias, an overwhelming preference, which gives time a direction that feels irreversible. Yet the origin of this arrow is still mysterious. If the fundamental laws are time-symmetric, why did the universe start in a low entropy state in the first place? Evidence from cosmology suggests that the early universe was extraordinarily ordered, almost perfectly uniform. This low entropy beginning provided the foundation for everything that followed. As the universe expanded and evolved, entropy increased, and the arrow of time was established. The universe's preference for disorder stems not from the laws of physics themselves, but from its initial conditions. This leads to a remarkable insight. Time's direction is not an inherent property of physics, it is a consequence of the universe's initial state and the statistical tendencies of matter. Broken coffee cups, spilled coffee, melting ice, and aging humans all follow the same rule. They unfold along the arrow defined by increasing entropy. The past is the direction in which entropy was lower, and the future is the direction in which entropy grows. When we consider this on a cosmic scale, the arrow of time links the everyday world to the deepest structure of the universe. Each shattered cup is a tiny reflection of a universal law. Each moment, each process, each system evolving toward disorder reinforces the same principle. The irreversibility of time, which feels so obvious in daily life, emerges from the overwhelmingly likely outcomes of particle arrangements. It is statistical, profound, and universal. Understanding the arrow of time reshapes how we see reality. It shows that what we experience as the flow of time is not an illusion, but a reflection of one of the most fundamental tendencies in the universe, the relentless increase of entropy. The broken coffee cup becomes not just a trivial observation, but a tangible demonstration of a law that governs everything, from the smallest atom to the largest galaxy. It is one of the simplest yet most powerful ways to glimpse the invisible hand guiding the universe's evolution. Now that we have explored entropy and the arrow of time, it is natural to ask what this means for the possibility of traveling to the past. Science fiction often imagines people stepping into a machine and suddenly appearing in a previous moment, perhaps to witness a historic event or undo a mistake. But when we examine this idea through the lens of physics, the situation becomes far more complicated. Traveling to the past would require reversing the arrow of time, and that means reversing entropy itself. Every process that has naturally evolved toward disorder would need to be undone. Every broken cup would need to reassemble. Every spilled drop of coffee would have to leap back into its cup. Every scrambled egg would have to unscramble. Even the air molecules that dispersed when the cup broke would need to return precisely to their former positions. The scale of this challenge is enormous. It is not just a matter of moving a few objects back into place. Every particle in the universe would have to cooperate perfectly to reconstruct the low entropy state of the past. The laws of physics do not forbid this in principle. Newton's equations, Maxwell's equations, and even the core rules of quantum mechanics allow for time-symmetric solutions. In other words, the mathematics permits a reversal of motion. But probability is what rules the physical world. The number of ways for a system to exist in a high entropy, disordered state vastly outnumbers the single, incredibly precise arrangement required to restore the past. Statistically, the chance of such a reversal occurring spontaneously is effectively zero. This is why we never witness entropy reversing on its own. We see broken cups remain broken, smoke remain dispersed, and ice continue to melt, even if we could manipulate every atom with perfect accuracy. The energy required to orchestrate such a reversal would be unimaginably large. Any slight deviation in the positions or velocities of particles would prevent the system from returning to its original state. The universe simply does not allow the past to be reconstructed, not because of moral rules or arbitrary restrictions, but because the statistical likelihood of such an event is vanishingly small. Entropy also explains why even our most carefully designed attempts at time manipulation are fundamentally limited. When we record events on video and play them backward, we see the apparent reversal of motion, but this is only a representation. In reality, the physical universe continues to evolve toward higher entropy. No machine, no technology, and no human effort can spontaneously decrease entropy on a universal scale to make actual backward time travel possible. Every act of reversing a process locally tends to increase entropy elsewhere, maintaining the overall forward flow of time. The broken coffee cup, in this sense, is more than a simple accident. It is a symbol of the ultimate impossibility of undoing the past. It demonstrates the universality of entropy, the arrow of time, and the statistical nature of reality. When we grasp this, we begin to see why our everyday experiences, from spilled liquids to aging bodies, all follow the same irreversible pattern. These are not just coincidences or conveniences. They are reflections of a deep and fundamental principle that governs the entire cosmos. The lesson is striking. Time travel into the past is not merely impractical or difficult. It is effectively impossible because it would require the universe to perform a statistical miracle of unimaginable scale. The broken coffee cup shows us that the flow of time is not arbitrary, that our past is firmly out of reach, and that every moment we experience is part of an irreversible march toward higher entropy. It is one of the clearest, simplest, and most profound examples of why the universe works the way it does and why the past, once lost, can never be regained. Even though the arrow of time explains why cups break and never reassemble, and why entropy increases, there remains a deeper question that continues to puzzle physicists. Why did the universe start in a low entropy state in the first place? If the laws of physics themselves do not favor a direction for time, why was the early universe so remarkably ordered? Observations from cosmology suggest that shortly after the Big Bang, the universe was hot, dense, and surprisingly uniform. Matter and energy were distributed almost perfectly evenly. The universe at that moment had extremely low entropy, meaning it was in a highly improbable, highly organized configuration. This low entropy beginning set the stage for everything that followed. As the universe expanded and evolved, entropy naturally increased. Stars formed, galaxies clustered, planets coalesced, and life emerged, all following the statistical tendency toward disorder. The broken coffee cup in your kitchen is a tiny echo of that same principle. The universe's initial state determined the direction in which time would flow and the way events would unfold on every scale, from atoms to galaxies. The fact that the early universe had such low entropy is astonishing. Why did it begin in such a special, highly ordered condition? Physicists have proposed several ideas, but no definitive answer exists. Some suggest that gravity may play a role. Gravity, unlike other forces, can create order even as it increases entropy in certain ways. When matter clumps under gravity, stars and galaxies form structured systems, even though the overall entropy of the universe continues to rise. Others propose that there may be deeper, unknown principles of physics that we have not yet discovered, governing the initial state of the cosmos and its subsequent evolution. The broken coffee cup is a perfect illustration of why this question matters. On the scale of everyday life, entropy explains why objects age, decay, or break. On the scale of the cosmos, it explains why the universe evolves in a particular temporal direction. Without a low entropy beginning, the universe might not have developed an arrow of time. If the early universe had started in a highly disordered, high entropy state, there would have been no preferred direction for events. Cups might not break in predictable ways. Stars might not form. The flow of time as we experience it might be completely different. This perspective changes how we see reality. Time is not an external river flowing independently of the universe. Instead, time is a reflection of the universe's statistical tendencies. The flow of time, the irreversibility of events, and the accumulation of disorder all emerge from the initial conditions set billions of years ago. The broken cup, the spilled coffee, the melted ice, and even human aging are all governed by the same principle that was determined at the very beginning of the universe. Acknowledging this also reveals the humility of science. There are aspects of reality we can describe and predict, like entropy and the arrow of time. But the ultimate reason the universe began in a low entropy state remains one of the great unsolved mysteries of physics. The broken coffee cup teaches us that some truths are accessible through observation, experimentation, and reasoning, while others, like the initial conditions of the cosmos, challenge the limits of our understanding. It is a reminder that even the simplest phenomena in daily life can connect us to the deepest, most profound questions about existence. In essence, the universe we observe, with its irreversible processes and forward-flowing time, is a product of the rare and delicate order present at the very beginning. Every shattered cup, every spilled drop, every spreading cloud of smoke is a small echo of that initial cosmic arrangement. Understanding this links the mundane and the cosmic, showing that the direction of time, the inevitability of entropy, and the impossibility of reversing the past are not separate mysteries. They are all part of the same fundamental story. Now let's return to the question of time travel and examine it in light of entropy and the arrow of time. In popular imagination, traveling to the past is often depicted as possible with a machine, a wormhole, or some futuristic technology. People imagine stepping backward into history, witnessing events, or even altering outcomes. But when we consider what physics tells us about the universe, time travel to the past becomes not just difficult, but effectively impossible. Traveling to the past would require reversing the direction in which entropy increases. In other words, the entire universe would need to move from a higher entropy state back into a lower entropy state. Every broken cup would have to reassemble. Every spilled coffee drop would need to leap back into its cup. Every scattered molecule would need to precisely return to its original position. The system as a whole would have to perfectly restore the highly ordered arrangement that existed at some previous moment. Even a tiny misalignment in the trajectory of a single particle would prevent the entire process from succeeding. The scale of coordination required is beyond imagination. Fundamentally, the laws of physics allow for motion to be reversed. Newton's equations, Maxwell's equations, and even the fundamental equations of quantum mechanics are time-symmetric. In principle, nothing forbids particles from moving backward in time. Yet in practice, the statistical realities of entropy dominate. The universe overwhelmingly prefers states with higher entropy because there are vastly more ways for systems to be disordered than to remain ordered. The probability of all particles spontaneously cooperating to reverse entropy is so extraordinarily low that it is effectively zero. Even if we could hypothetically manipulate every particle with infinite precision, reversing entropy on a universal scale would require an incomprehensible amount of energy. The slightest deviation in timing, position, or motion would ruin the attempt. This explains why, in our everyday experience, we never witness objects spontaneously becoming unbroken, smoke returning to a candle, or melted ice cubes reassembling. Every natural process adheres to the forward flow of time, reinforcing the arrow of time dictated by increasing entropy. This also clarifies why local attempts at reversing time are fundamentally limited. In a laboratory, we can create controlled systems where entropy appears to decrease temporarily, such as carefully sorting particles or cooling a system. But any decrease in one localized area is always accompanied by an increase elsewhere, keeping the total entropy of the universe moving forward. Time travel to the past is not just about moving objects backward. It would require orchestrating the motion of every particle in the universe to reconstruct a previous low entropy state, which is statistically impossible. The broken coffee cup becomes a simple but profound symbol. It illustrates the universal principle that the past is fundamentally unreachable. It is not a technological problem. It is a statistical law. Every shattered cup, every spilled liquid, every aging system reminds us that the arrow of time points only one way. The direction of time, the irreversibility of events, and the impossibility of undoing what has already occurred are direct consequences of entropy and the low entropy beginning of the universe. This understanding reshapes how we think about reality. Time travel to the past is not merely improbable, it is effectively forbidden by the fundamental statistical structure of the universe. The past once experienced is lost forever. Every process in our world, from the mundane to the cosmic, follows the same irreversible pattern. The arrow of time, as revealed by the shattered cup, is one of the clearest signs that the universe has chosen a direction, and we, along with every event and object, move along it without exception. It is a quiet but profound truth that governs everything we observe, reminding us that reality is not arbitrary, but deeply structured by the laws of probability and the relentless march of entropy. Even though entropy and the arrow of time explain why cups break, coffee spills, and ice melts, physics remains honest about the limits of our understanding. There are still profound questions that we cannot fully answer, and one of the deepest concerns the origin of the universe's low entropy state. If the fundamental laws of physics are largely time-symmetric, Why did the universe begin in such a highly ordered, low entropy condition? Observations from cosmology suggest that the early universe, shortly after the Big Bang, was incredibly uniform, hot and dense, yet strikingly ordered. This initial order is what allowed time to develop a preferred direction and set the stage for the evolution of the cosmos as we know it. The universe's low entropy beginning is not just an abstract detail. It has concrete consequences for everything we see. It explains why stars form from gas clouds instead of dispersing randomly, why planets coalesce from cosmic dust, and why life can emerge and persist. It also explains the everyday events we take for granted: the broken coffee cup, the spilled coffee, the melted ice, and the aging of living organisms. Each of these processes is a direct consequence of the universe starting in a special state with low entropy. Without that initial order, there would be no arrow of time. The universe might look completely different, and events could unfold in ways that seem completely unpredictable or even chaotic to us. Physicists have proposed various ideas to explain the low entropy beginning, but no definitive answer exists. Some suggest that gravity plays a critical role. Gravity has a counterintuitive effect. While it can increase entropy in general, it can also create local order by pulling matter together to form stars and galaxies. Others speculate that there may be fundamental principles or laws of physics that we have not yet discovered, which dictated the initial conditions of the universe. Some researchers even entertain the possibility that our universe is one of many in a larger multiverse, where different regions could begin with different levels of entropy, and we happen to exist in a region conducive to life and order. The broken coffee cup offers a tangible way to understand this cosmic principle. On a tiny scale, the cup shatters and entropy increases. On a cosmic scale, the universe evolves similarly from an improbable, highly ordered initial state toward a vastly more probable, disordered configuration. The principle that governs the shattering of a cup also governs the formation of galaxies, the death of stars, and the long-term evolution of the cosmos. It is a striking example of how the same statistical rules apply across all scales, linking the mundane and the cosmic. This perspective also brings humility to our understanding of reality. Some aspects of the universe are within our grasp. We can measure entropy, observe the arrow of time, and predict the behavior of large systems. Yet the ultimate reason why the universe started in a low entropy state remains a mystery, one that challenges even the most profound scientific theories. The broken coffee cup reminds us that even the simplest, most ordinary phenomena can point to the deepest and most mysterious truths about existence. In this sense, every shattered object is more than a trivial accident. Each one is a window into the statistical rules that govern reality, the initial conditions that shape the universe, and the irreversible march of time itself. By studying the broken cup, we are indirectly studying the cosmos and the subtle principles that have guided its evolution from the very beginning. It shows us that the ordinary events of daily life are intimately connected to the extraordinary history of the universe, and that the flow of time, as relentless and irreversible as it seems, is rooted in the fundamental nature of existence itself. Imagine watching a film of the universe from the very beginning. The Big Bang, the formation of the first stars, galaxies clustering into vast cosmic webs, planets coalescing from clouds of dust, and eventually life emerging on one small blue planet. Over billions of years, stars burn their fuel, matter spreads, and time flows in a seemingly irreversible direction. Now imagine taking that film and playing it backward. Suddenly, the universe appears strange and alien. Stars would unburn, gas clouds would contract, galaxies would converge, and planets would unform. Smoke would gather itself back into cigarettes, spilled liquids would leap back into their containers, and broken coffee cups would reassemble perfectly on tables. Every event that we perceive as natural and inevitable would look like a bizarre and highly improbable miracle. At first glance, nothing in the reversed film directly violates the equations of physics. Newton's laws still describe the motion of objects. Maxwell's equations still govern electromagnetic fields. Even quantum mechanics allows for time-reversed possibilities. Yet the reversed universe feels wrong. Our intuition rebels because it is tuned to the statistical tendencies of entropy. We recognize that the reassembly of broken objects, the contraction of smoke, and the unspilling of liquids are astronomically improbable. The universe in reverse would require an almost impossible coordination of countless particles, each moving precisely in the correct direction, at the correct time and with the correct energy. Any deviation, no matter how tiny, would prevent the process from succeeding. This thought experiment highlights the deep connection between entropy, probability, and the arrow of time. While the fundamental laws of physics are largely time-symmetric, the statistical behavior of large numbers of particles is not. Forward in time, entropy tends to increase because there are far more ways for systems to be disordered than ordered. Backward in time, the probability of spontaneous decreases in entropy is effectively zero. The universe overwhelmingly favors the forward direction, and this is why we never observe macroscopic events reversing themselves spontaneously. The broken coffee cup becomes a simple yet powerful illustration of this principle. The cup's shattering is an everyday event, yet it embodies the same rules that govern the universe on cosmic scales. Just as stars form from clouds of gas and galaxies cluster into larger structures due to statistical tendencies, the coffee cup breaks because disorder is overwhelmingly more probable than order. The motion of countless microscopic particles ensures that entropy increases and the cup remains broken. This also provides insight into why time feels irreversible to us. Our memories, perceptions, and experiences are all organized along the arrow of time. We remember the past because it was more ordered and predictable. We do not remember the future because it has not yet been realized and exists in a higher entropy state with countless possible outcomes. The reversed film is a useful illustration, but it is not reality. The probability of such a reversal occurring in the real universe is so vanishingly small that it can be considered impossible. In contemplating a universe running backward, we gain a deeper appreciation for the everyday arrow of time. Ordinary events like a coffee cup falling and shattering are not trivial. They are expressions of universal statistical laws that apply to every system, from the tiniest atom to the largest galaxy. Watching the film in reverse emphasizes just how extraordinary the order of the past was and how the relentless increase of entropy shapes every moment we experience. The broken cup, simple and familiar, becomes a window into the deepest structure of reality, revealing why the past is fixed, the future is uncertain, and the flow of time is one of the most fundamental features of the universe.